is Miroslav Ponec. He's an engineering director, a protocol optimization, media, and carrier division from Akamai Technologies, and he's going to be talking about making video streams quicker.
Is it better? Okay.
You might want to move your mic up a little bit.
Okay. So wake up, everyone. Now I'm going to tell you how to make your video streams quicker. So before we do that, well, we are all on a journey that leads to better video streaming experience. And I've been on a journey last week, and I took this beautiful picture. So let me tell you a little bit about the history of innovating the internet transport protocols. And I'm really happy that Ali has done a great job in the morning in the tutorial to give you the foundation and some details about TCP. So the TCP protocol has been invented, as Ali mentioned, way back, so more than 40 years ago, and it has been evolving steadily over the years, and it became the #1 transport protocol on the internet, and we are all using it for our video streaming and a lot of other things on the internet. So what has also happened is that the protocol has ossified. So by ossification, we are referring to a process of becoming rigid, like a bone. So basically for TCP, this means that, well, you cannot make changes anymore. You cannot innovate. If you release a new spec or you want to make some change to the protocol, it's going to take years and sometimes decades to be able to deploy those changes. So that's a major problem. It doesn't mean that we are not able to make any changes to the protocol. The TCP, or Transmission Control Protocol, is a protocol that still allows some changes that could be deployed, for example, on the server side only, and that's mostly congestion control algorithms. That just determines how quickly the server is pushing packets to the network. And since we mostly control the servers very tightly, then you can decide on that rather easily. So some of these problems with innovating the transport protocols on the internet, that's just a well understood big challenge. And we do have UDP to the rescue. So UDP is another protocol, an alternative to TCP. It stands for User Datagram Protocol, and it provides bare minimum functionality. So it pretty much just implements only getting data from point A to point B over the internet, but nothing else. So everything you want to do in order to make your protocol and the data transfers for your videos to work well, you just have to implement it yourself on top of the UDP protocol. And UDP protocol, similarly to TCP, is well supported by the public infrastructure, by all the routers, all the end user devices, and all of the operating systems. So with that, you can actually just implement everything yourself in a way you like, and that allows the innovation. So with TCP, if you want to deploy a new change, you would run into compatibility issues with all of the devices and routers out there because they rely on the very details of the implementations of TCP. With UDP, you don't have the problem because you implement everything on the layer above. So another trick that you could use with UDP-based protocol is that you can encrypt everything and also authenticate the pieces that don't have to be encrypted. That means that then nobody on the network and all the middle boxes on the internet aren't able to see the data or be tampering with it. So that's, again, another step that allows you to innovate. And there is companies that like Google or Akamai and many others as well who have identified this problem with sort of using a TCP protocol that's been out there for ages. And in response to that, they have introduced their own proprietary protocols on top of UDP. And in order to do something better and more scalable, we actually focused on working together in an open community and as part of standards, since most of the crowd is actually interested in standardization and specifications. So we started collaborating as part of the Internet Engineering Task Force working group on a protocol called QUIC. And QUIC stands for Quick UDP Internet Connections. And it's a protocol that will allow us to have a common standard for a UDP-based transport on the internet. So how is this relevant? Why am I talking here about this, and how is it relevant to video? So as a single data point, let me tell you that last year when Vimeo used the QUIC protocol on the Akamai platform, they have immediately started seeing improvements to all of the relevant video metrics. So their users have been seeing fewer rebuffers, faster startup times, higher bit rates, and throughput. So generally, with transport protocols, you can achieve better performance for the video streams. So I have seen that there have been no graphs so far today, so let me give you one. And this one is a complex one. So specifically, it is a complementary cumulative distribution function of throughput, so CCDF. And what it means is that on the y-axis, I'm just going to let you be ready to read the complex graph first. So on the y-axis, we have percentiles of users. And on the x-axis, and please note that this one is in a logarithmic scale, you have the throughput, so the speed of data transfer in megabits per second. So then we see two lines in here. The orange one represents the performance we have been seeing with the QUIC protocol, and the blue line represents TCP. Also, the shading around the lines is the statistical error bounds. So this example and this measurement is from a recent soccer event, and we have been able to achieve a 25% higher throughput for the median viewer. So when I say median viewer, that means the 50th percentile for users, so that would be right here, and you can see the improvement over here. So the distance between the lines, the blue one and the orange one, is on the horizontal line. That means the increase in speed. So you could read over here that this is an increase of 25%. And also, if you look at the vertical distance between the lines, that gives you how many users were able to achieve faster speed. So any point on the line on the graph will tell you which user or how large percentage of users is able to achieve that speed or faster. That's why this is always going from 100% of users down to 0, because as the speed increases, there is fewer users who can achieve that speed. And we are commonly seeing results like this. It does not mean that QUIC is a magic or miracle. It still uses the same networks, and also, as you may have seen in some of the prior presentations, the goal of the protocol is not to be aggressive and push out all the other traffic on the internet. Akamai clearly cannot do that because of that scale. We would be pushing out our other traffic mostly out of the network. So basically, what you could do is that you could modernize or innovate in the protocol and utilize the network better. So QUIC is intended to be helping with applying some modern and new things to running the network at the maximum utilization. So now that we know that we do have some protocols that are modern and better and could achieve better performance, how do we actually get some benefit out of it? How do we get users to use it and enjoy the benefits? Well, you need the servers to support the protocol, you need the clients to support the protocol, and then you also need to actually have someone to use that protocol for the video distribution. So Akamai has been doing this since 2016, and we have only had a handful of customers who actually opted in, like Vimeo, for example. So a better, more scalable approach that we are taking now is to just enable QUIC protocol for everyone by default, and if you don't like it, you could opt out if you wish. So that's actually possible because of the design of the protocol. With QUIC, you do not have to modify your video players or your workflows, your DRM, or any other video aspect, because this lives in the lower layer, just transporting the bytes over the internet. So you could replace this protocol for QUIC and get the better performance without any modifications to your existing workflows. So how is that actually possible? So how does QUIC make this happen? So with QUIC, there is many different optimizations and innovations in the protocol, and I would like to just highlight a few. The important one is low latency connection establishment. It's very relevant to, for example, the low latency streaming. If you utilize HTTPS to transfer your video segments or audio segments over the internet, then you are applying TCP together with the TLS for crypto. So these two protocols are applied, and whenever you want to establish a connection, you have to have a lot of sort of chatty transfers between the client and the server. So there is a lot of back and forth until the first video request goes to the server and the server replies back with the data. So the usual setup for HTTPS takes 3 or 4 round trip times. So it just has to go back and forth 3 or 4 times before there's anything useful happening. So with QUIC, what we are seeing is that about half of the connections could use 0 round trip time connection establishment. 0 in here means that there is just no delay at all. The very first packet coming from the server, from the client to the server already contains the request for the video, and the very first packet coming from the server to the client already contains the first piece of the video. So there is just no extra latency at all. This only applies if you had some communication between the client and the server before. If you didn't, then there is a single round trip time introduced for the client to exchange some crypto stuff with the server. So this really greatly reduces the latency. QUIC protocol also has smarter loss recovery, and that's possible because it conveys more information about the timing of packets that may have been lost. Sorry. So I have seen in the presentation by Ali in the morning that there is Headofline blocking issue in TCP, and the solution that has been proposed in there was to use the 3-lane highway, which would be use multiple TCP connections. With QUIC, you do not have to do that, especially that it comes with some unpleasant impact on fairness on the network. So with QUIC, it's a multiplexed protocol. What it means is that you can have multiple different requests and responses flowing in parallel over the same QUIC connection. So all of that is happening, and it's without the head-of-line blocking issue. So the head-of-line blocking issue, as mentioned in the morning, is that if one request is being satisfied, so you make a request for a segment, and you are getting data of that segment back from the server, and one of your packets of that segment gets lost, what happens with TCP is that just everything stalls and waits. So you cannot, like all of the other requests that have been actually progressing and you are still getting the data, they cannot be actually relayed back to the application or the video player. So everything just waits. That's the head-of-line blocking issue. With QUIC, that's not happening anymore. So QUIC just overcomes that, and only the actual lost packet is stalled and waiting. Everything else is progressing. QUIC also has a very nice feature, which is called connection migration. So if you just use your phone and you roam from, let's say, one ISP to another, for example, if I connected to Wi-Fi and then I suddenly went out onto the street, I lose my Wi-Fi connectivity, I switch to cellular. Well, what happens with TCP is that you just lose your connection right away. The video stream gets broken, and if the player is smart, it will retry. So it has to re-establish the connection again, go through all of the 3 or 4 round-trip times, as I mentioned before, and it sort of wastes the time on retrying and reconnecting and sort of starting from scratch. With QUIC, you can keep going between different ISPs, between different networks, and it just seamlessly continues. So there is no interruption at all. This is sort of seamlessly supported. And a very key point is that with QUIC, you could actually experiment with all of these features and with various optimizations, since it's in the application layer and we can easily upgrade our applications on most of our phones and other devices. Just updating an app is really simple. So we could make different experiments and just change versions of the protocol very rapidly. And At Akamai, we don't sort of just say, oh, Quick is better, so we will use it for everything. That is not actually true. What we are saying is that it expands the tool set significantly, and we are applying it where it makes most sense. So there are networks and certain use cases where Quick provides great benefits, as I shown before, some of the numbers. And sometimes it doesn't. And also, there is no single protocol like Quick or TCP. At Akamai, we have many different implementations of Quick and many different implementations of TCP, and those are actually not just some random settings. These are very key algorithms in the protocols that we choose between. So whenever you see me comparing some numbers between TCP and Quick, these are the most optimized versions that we applied to each user request. So for each user request, we just choose the best one that we know from historical data sets. We just choose what works best for that case. So with Quick and the standard likely coming, the first version of the standard from IETF likely coming later this year, we are expecting that Quick as a protocol would become ubiquitous on the internet and supported by all devices, all the platforms, all the browsers. And there is a good potential that it may replace the TCP as a main transport protocol. It is already 7% or estimated to be 7% of the current internet traffic. So this is really substantial. You are very likely using Quick without knowing it today, or maybe you already know. And it is not just for HTTP use cases. If you want to stream your videos, what you have to use first as part of your workflow is DNS. So you have to find out what server to connect to. And DNS already uses UDP, but it could do that more efficiently with Quick and get both more efficient, but also due to Quick being always fully encrypted, it could give you some additional nice privacy guarantees that you aren't getting today. Also, some of the low latency streaming is utilizing a WebRTC protocol. We have seen the spec on the slides before from multiple speakers today. So WebRTC could also utilize Quick as the underlying transport to be more efficient, and there are already experiments underway to do that. So I'd like to finish where I started today. So that's the Forrest Gump scene. If there is just one single thing to remember from my presentation, I would like that to be that Quick is out there, it's available today, and it can help you improve your video streaming experience and make your streaming quicker. So as long as you are using it already, or you have a plan to use it, then everything is great. And if you don't, I would like to use my favorite quote from an Akamai co-founder, Danny Lewin: "You are behind." So thanks a lot, and thanks for the organizers for having me here today.
Thank you. Let's go ahead and open this up to questions.
Thank you. Can I ask two questions? The first question is, what I'm hearing is the Quick is providing an alternative to TCP's congestion mechanism. Do you believe that Quick's advantage is more on the video transmission, or you think this is applicable to any video, any web content? So that's my first question. Second is, I think I recently checked that the Quick's traffic is like 1% of the total video total internet traffic, so the adoption rate is pretty low. So do you think it's because only Chrome supported? I'm not aware of other clients supported.
Okay, those are great questions. So the first one was about its applicability. So Quick is an underlying transport protocol, and it could be applied to all internet transfers, majority of use cases. So for the web, absolutely not just video, but also just the websites. But it also has vast applications to, for example, WebRTC, DNS, and many others. So it is the underlying protocol like TCP, and it could be used in many different use cases. The second point was about Oh, you've mentioned 1%, so I believe the current estimate is 7%, and the reason why it's still so low, actually 1% of the internet traffic is enormously giant number. So I wouldn't call it low, and also if you, for example, look at IPv6 adoption, that's another evolution on the internet. Well, you know how long it has been taking, and you know where we still are. So QUIC has like a really quick ramp up in terms of adoption. And the main reason, at least from my perspective, the main reason why it's still not being used, let's say 50% for 50% of the traffic is that we are mostly all waiting for the first standards to be out there. Because right now, I've mentioned rapid iterations and rapid experimentation for the protocol. And it is indeed the case today. The protocol is changing pretty much every month. And it's becoming sort of not compatible with the prior version. So if you want to keep up, this is really hard. So everyone is waiting for the first standard to be out there, such that there is something that stays and you can implement it and sort of have that as a sort of something that's stable and supportable on your platforms, which cannot be updated so regularly. So it is really the main reason. It is evolving so rapidly that keeping up with the rate of changes is too hard. So I believe by end of this year we will have the standard out there, and this will all change.
We'll take another one in front, and then I'll go to the back.
Yeah, well, actually, you answered a couple of my questions just now. I'm trying to understand what the pace of adoption would be. You mentioned that you think the standard will be published this year. Where is the standard being published?
Sorry?
Where is the standard being published?
So it's part of,
IETF.
yeah, there is IETF working group working on QUIC, and it's hopefully going to be published by end of this year.
And when you talk about 1 to 7, whichever 7% adoption, is that somewhat of a kind of a closed ecosystem? It's like certain people are adopting it on both ends, or can you speak to who's doing that?
So right now the state of QUIC usage is mostly Google's services. So Google, both server side and client side in terms of Chrome, is supporting it. There is also a lot of open source implementations that you could use on the client side, but most of the 7% would be Google's traffic and YouTube specifically. And Akamai, we are talking about less than 1 terabit per second. That's what we got close to recently.
Are you using Google's implementation at this point?
Yes, Akamai is using the Google QUIC version, and we always keep being compatible with the Chrome browser. So we want to be able to be compatible with the client side. That's correct. So there is a delay between the new drafts of IETF QUIC.
You mentioned some work happening around WebRTC over QUIC. I'm curious, are there mechanisms in QUIC to control the loss recovery and reliability mechanisms to actually have kind of unreliable real-time delivery?
Mm-hmm. Yeah, that's a great point, and as part of the first version of the specification, it's not going to be there, so everything will be reliable because it pretty much replaces TCP and TLS where everything has to be reliable. But the actual implementations, and I've mentioned that people are already experimenting with WebRTC, the actual implementations have partial reliability, so you could actually have some losses tolerated. But that's for experimentation, not for the first version of the standard. So the first version of the standard will not have that, but we are already experimenting with it, and some next version will have it. There was a question from.
Is QUIC enabled on Akamai as a whole or a specific sub-network? It's available generally.
Yeah, that's also another great question. So for security reasons and compliance reasons, we have enabled QUIC broadly for all of our media customers whenever the customer uses an Akamai wildcard certificate. So whenever there is something.someakamaidomain.com, but if a customer uses their own TLS certificate, then they actually have to click a single checkbox to enable QUIC to sort of say, okay, I want my certificate to be using this crypto in QUIC, because QUIC combines TCP and TLS features, so it has the crypto built in. And it has not yet switched to TLS 1.3, the latest TLS standard. Once it does, it will probably be a different landscape, and it may be much easier to just enroll everyone.
The last question. Can you also elaborate on the forward error corrections, if it will be part of the standard, and what forward error correction technology will be used as a part of the standard, if it will be?
So forward error correction is unlikely to be part of the first standard. I would say it won't. But there are already experiments underway to experiment and see whether there is actual benefits in it. There have been some super basic experiments with FEC, which was just like an XOR of 2 packets, like something really, really basic, and it has not led to any good results. So being more aggressive on retransmitting lost packets has actually proven to be more efficient. So there are experiments with some really state-of-the-art latest FEC schemes which are using some windows of recent packets, and those are promising. At Akamai, specifically for media use cases, we have seen that FEC could provide major improvements, for example, for the ingest of the video, where you really care about that single stream to get to the other side very reliably. So this may also depend on the use case. So ingest is different from just the broad distribution from, let's say, a CDN to many users. Yeah.
All right, thanks again.